Bias-variance trade-off, overfitting and underfitting are common challenges in machine learning that can significantly impact the performance and accuracy of a model. Now, in this video, we're going to look at what these terms mean and how to avoid them. So bias-variance trade-off, we can define bias as the difference between the average prediction of your model and the correct value which you're trying to predict. Now, the high bias models have a tendency to underfit the data. Why? Because, a model with high bias pays very little attention to the training data, thus oversimplifying the model. Okay. So especially here, this results in high training error and poor performance on unseen data. Now, when we look at variance, this is the variability of your model prediction for a given data point, or a value that tells us the spread of our data. Now, a high variance here, in this case, when you have a high variance model, it has a tendency to overfit. Okay, here overfitting, here was underfitting. So it has a tendency to overfit the data. Now, this will result in low training error, right, from your data set, training data, but high error on unseen data. Okay, now, in this case, a model with high variance pays a lot of attention to the training data. What that means, it fits so closely to your training data that it doesn't generalize on data which it hasn't seen before. Now, the goal of machine learning here is to find a model that has low bias and low variance. This is a very challenging task, and trying to get a balance between the two is what you need to strive for. Now, the bias-variance trade-off essentially is just a sweet spot where a machine learning model performs between errors introduced by bias and variance. Now, let's look at an example here. So, for example, if you increase the number of features or increasing the depth of your decision tree. So let's say this is your decision tree. So usually decision tree, we can look at it as an upside down tree, right? So here we have your node, right? So this is your root node, and again, these are your leaves, right? So in this case, for example, here, if you increase the depth of your decision tree, this will increase the model's complexity and reduce the bias. But now, when we dial this, or we increase the variance in this case, right? Reducing the number of features or decreasing the depth of this tree will decrease the model's complexity and reduce the variance. Okay. And thus this will increase the bias. Okay, so that's just an example of how the challenge of trying to balance between bias and variance. Okay. So again, here we can see in underfitting we have low complexity, high bias, low variance, right? Again, here overfitting, you have a complex model, meaning that high variance, low bias on your training data, but high variance on your test data. Okay, and this also has high bias on your training data, but on unseen data, there's low variance. Okay. All right. Again, here, this is the the classical challenge, right? Trying to balance between underfitting and overfitting. So the best fit is something that is in the middle. Okay. All right. So what's underfitting? All right. So underfitting in this case is when you train your data, or rather underfitting the training data when the model performs poorly on the training data, right? This because the model is unable to capture the relationship between the input examples. Sometimes we call the input X, right? And again, the target value, often called Y. So Y is our target value. So this model fails to capture the relationship between the X input. Okay, so remember this formula, we apply a function on X, right? And we have our Y here, okay? So it fails to capture that relationship. Underlying, as you can see here, there's still some yellows on this other side. The goal with classification, you want to distinctly categorize these classes, separate these classes distinctly. Okay, so in the case of underfitting, our training test error is high. Okay, what that means, we'll have high bias, right? And our test error is also high, right? That means it will have high variance. So as you can see here, let me just erase this. So let me take this out of the way. So as you can see here, with underfitting, we're saying that it has high bias and low variance. Okay. Let me put the pen here again. All right. So in summary here, we can see underfitted model have low variance and high bias. So how do we avoid underfitting? So the first thing here is to use a complex model, right? Using a complex model with more capacity to fit the data can help prevent underfitting. Another approach is to create new features, right? We call this feature engineering, right? So here you want to transform existing features, right? Or create new features to capture more information about the relationship between the feature variables, our X, and the target variables, our Y. That can also help in preventing underfitting. Again, the third one here, so you want to decrease regularization. Regularization here is a parameter, hyperparameter, that tries to, again, here you can use different techniques like L1 and L2. Here it just penalizes a model. So when you reduce this amount of regularization, it can allow you to fit the data more closely and prevent underfitting. And then also you can increase the size of the training data. What that means is a larger training set provides more information, okay, for the model to learn from, okay, and this will help with, preventing underfitting. And then also you can increase the number of features, right? Meaning not only just increasing the number of features, you want to increase relevant additional features to the training data. And lastly here, we can also use ensemble methods. What this means, you're combining multiple models to produce a final prediction. So for example, here, some techniques, we have bagging, we have boosting, right? And random forest is a good example. Random forest is a good example of an ensemble classifier. Okay. For example, here you can use, it just uses the idea of wisdom of trees. You use several decision trees. So all these are aggregated. The performance of all these decision trees are aggregated, and then we get the prediction from multiple models. Okay. Now let's look at what is overfitting. Okay. We say overfitting occurs when a model fits the training data too well and has poor generalization performance on unseen data. Okay. So this is because the model is memorizing the data it has seen and unable to generalize on unseen data. Okay. Now, in the case of overfitting, in fact, let's just see that. You can see here, it fits so perfectly. It tries to, discriminate these two classes, the blue X and the, yellow circles, right? In this case, we say the training set is less, our training set error is less, right? So it will have low bias, and the test set error is high as well, meaning high variance. So if you look here, we're saying here it will have low bias and high variance, right? So in a nutshell, we're saying that both overfitting and underfitting lead to poor prediction on new data sets. Okay. So how do we prevent, how do we avoid overfitting? So using a simpler model, meaning having less capacity to fit the data, this can help to mitigate overfitting. And then also here, increasing or having a large training set, right, provides more information for your model to learn from and can help prevent overfitting. And here we call this regularization, where you add a penalty term to the model's loss function. Okay, what that means, it will just discourage large weights, and complex models, thus, helping to reduce overfitting. Some of the common regularization technique, we have L1, sometimes we call this lasso, and then we also have L2, again, we call this bridge regression, right? Again, we can use cross-validation. This is just a technique to split the data set into multiple folds and then training the model on different folds, right, to get a more robust estimate of the model's generalization performance. Early stopping, for example, if you're using a deep learning architecture or network, again, here, what that means, you monitor the performance of the model, right, on some validation test or validation set during training. And then you stop the training, right, process when the performance of the validation set stops or stops improving. There's no significant improvement, right? So you stop the training and record the performance. Feature selection here, again, here, you're just removing the irrelevant or redundant features. So for example, you perform what you call correlation analysis. You can remove those irrelevant features, or you use maybe a p-value. Okay, those that don't meet that threshold, you can remove it from the training data. And we have different ways of doing that. We can use something called forward or backward stepwise, selection methods. And lastly, here we can also use ensemble methods, right? Like bagging and boosting, right? For example, random forests can help reduce overfitting by aggregating the prediction of multiple models. All right, and then here, how do we detect underfitting, right? Again, here we can use validation curves and learning curves. Again, these curves helps to plot the model performance, right, on both the training and validation sets. So again, if we have underfitting, this will just show low performance on both training and validation sets. Okay, meaning there's a small gap between the two. Okay. Again, when we have high bias here, high bias models have a strong assumption about the relationship between the feature variables and target variables. Okay. Again, this can lead to underfitting if the assumption is not corrected. Okay. Again, high training error here. Model with high training error has a poor fit to the training data. Okay, this might be endemic of underfitting. So in conclusion, we can say that underfitting and overfitting are just some of the common challenges in machine learning that can significantly impact, all right, the performance and accuracy of your model. Okay. So again, here, just underfitting is just when the model is too simple to capture the underlying patterns in your data. This can result in poor performance. All right, poor performance on both training and test data. While overfitting here, we are saying that this occurs when the model is too complex, all right, meaning that it just becomes too closely fit to your training data. And in this case, it might even capture noise in the data. This also might result in a poor performance to new or unseen data. Okay, so in summary here, these are just underfitting and overfitting are just important consideration in machine learning, right? And addressing these issues or challenges or problems is very crucial to building an accurate and effective model. Okay, so again, the issue of bias variance trade-off, finding that sweet spot, okay, it's more like a skill, right? You want to balance the model complexity using different techniques like cross validation. We looked at that. Again, with that, there's a high chance you can improve or achieve good performance, right? And in that case, it might lead to accurate prediction on new data. All right, that just wraps it up.